Hello, Honors Pre-Calculus students. This is Ms. Cronky, and we are going to be covering Chapter 9, Section 2, all about arithmetic sequences and series. So one important thing to know before we get into Section 9.2 and then tomorrow also 9.3, we're going to be focused on the arithmetic and geometric sequences, which all kind of conform to the same pattern, and so that makes it a lot easier to write the rules. So yesterday when we were trying to come up with the rules for our sequences, we were really thinking outside of the box. Once you identify something as arithmetic or tomorrow geometric, you can really put it back into a box, and that makes it easier to write. So let's go ahead and get started with the definition for an arithmetic sequence. An arithmetic sequence is any sequence where the difference between consecutive terms is constant. So a few really important words here. Difference is implying subtraction between consecutive terms, so those are terms that directly follow each other, one right after another, and the difference between those consecutive terms must be constant. So that means the difference between two terms that come right after each other is always the same. Okay. Down below that I have some subscript notations to kind of show what that looks like. So I start off with a sub 2 minus a sub 1. That's the second term minus the first term. Whatever that difference is, it has to be equal to the next set of consecutive terms, a sub 3 minus a sub 2, or the third term minus the second term. And that just continues as you go up the sequence. The fourth term minus the third term, so on and so on. So in subscript notation, we could really write this piece right here as a sub n, the nth term, minus a sub n minus 1, the term that came before it. And those things are always equal to d. So they're all equal to the same thing. We're going to call that d, and you may remember from Algebra 2, we call that a common difference. So the number that you're adding or subtracting every time in this arithmetic sequence, that's going to be d. That's called your common difference. And that's really important when we're writing the equation or formula for a arithmetic sequence. Let's go ahead and look at what that formula or rule will look like. This is the formula or rule for an explicit arithmetic sequence. Of course, we could do recursive like we talked about yesterday, but here we're talking about I could easily find any term. All right, I'm going to give you two versions of a rule just really quickly. The first one is not necessarily the one that I'm going to be using, but you may have seen this last year in Algebra 2. It looks like a sub n equals a sub 1 plus the quantity n minus 1 times d. And so in this particular rule, you would need two things to be able to plug in. You'll need your first term here for a sub 1, and then you'll need your common difference for d. Substitute those values in. And the n and the a sub n, those remain variables in your rule, so that we could then plug in any n and get the nth term. So if I want the 10th term, I plug 10 in for n, and I'd be able to find a sub n. Now, I don't really like that one just because when I think about arithmetic sequences, I think about linear graphs or discrete graphs. And so I want mine to look immediately like the equation of a line because I know that to be arithmetic. And so my rule looks something like this. A sub n equals, and then dn plus c. So what I want to be able to do is plug in to this rule. Of course, I want to know the common difference between two consecutive terms. So there's my common difference. And then I also want to plug in for whatever this c value is. So I'm going to say below this rule where c equals a sub 1 minus d. So I just like it because that's finding kind of like the y-intercept of my linear function, like the b in mx plus b. And so all I have to do is take the first term, subtract the difference from it, and it gets me to what would have been the term if it was n equals 0. So I'm going to plug whatever that value is in for that c right there. Okay. And again, in that rule, n and a sub n would be like the different ordered pairs for whatever numbered term you're trying to find, and then whatever that term actually is. Now I've got directions here at the bottom of the screen saying we're going to find a formula for the nth term, a sub n, of the following sequences, and those are going to be on my next slide. So you can kind of fill in with me as I work. We're going to start with a sub 1 equals 15 and d equals 4. Okay, so I'm given the first term and I'm given the value of d, or the common difference. So I'm going to go ahead and use my rule, which is a sub n equals dn plus c, where again c is equal to a sub 1 minus d. So I know a sub 1 and d here. I would go ahead and say c is equal to 15 minus 4, or 11. And then I can plug in to find my rule. A sub n equals d, 4 times n plus 11. Now, if I plug 1 in for n, or I get the first term, a sub 1 equals 4 times 1 plus 11, and that's equal to 15. So I can kind of check it works for that specific term. Okay, and then it's going to be increasing by 4 each time, so that follows along with the constant difference. That one's pretty easy. In the second example, I'm given the 9th term, a sub 9, is equal to 130, and the 15th term, a sub 15, is equal to 40. So what I'm seeing from the 9th to the 15th term is that my sequence, or the terms in my sequence, are decreasing. So I'm thinking ahead of the game here, my common difference is going to be negative. But I make a big jump from the 9th to the 15th term. So what I need to do is think about this sort of like a linear function, and I really want to find the change from one term to the next. Think about slope. Okay. So what you want to do for this to find the common difference is find the difference between the terms. Actually, I'm going to do the later term, although it wouldn't really matter. I'm going to do the later term 40 minus the earlier term 130. And so I can see there that my difference is going to be negative 90. Okay. But that was not in a single jump. I went from the 9th to the 15th term. So how many jumps, or how many terms did I take right there? 15 minus 9, the later term minus the earlier term, would give me 6. And negative 90 divided by 6 is negative 15. So I can find my common difference if I treat my common difference like my slope, okay, that constant rate of change. So once I have the common difference, I can go ahead and think about my rule. A sub n equals dn plus c. And normally I would say where c is equal to a sub 1 minus d. But the thing about this particular example is I don't know what a sub 1 is, the first term. So in cases like this, and if you have a formula, you can pick either term. It doesn't matter which one you choose. So for example, I may pick the a sub n and the 30, and then think about what that is as an n a sub n ordered pair. So the value of n is 9, the a sub n, or the value of the term, is 130, and then I can plug those things in for n and a sub n in my formula. So I'm going to go over back to my formula over here that I like to use, and where I see a sub n, I'm going to substitute 130. My difference I found by calculating essentially the slope, common difference, between the terms is negative 15. Multiply that by my n, which is 9, and then add C. So calculate negative 15 times 9. That'll be negative 135 plus C. And then add 135 to the other side. So C is equal to 265. So now I have D is 15. I know C is 265, and I can plug those into my rule. So A sub n equals negative 15n plus 265. If you're unsure if your method works, something that you could do is just check either the 9th or the 15th term. So I could check, maybe I'll just check the 15th term. Okay, so I want to calculate A sub 15 with my rule. That would be negative 15 times 15 plus 265. Negative 15 times 15 is negative 225 plus 265. And then that tells me that the 15th term, A sub 15, is 40. So that checks out with what I was given in the problem. Now you can use the other formula if you're more familiar with that formula from Algebra 2. And there are other ways to think about sequences. That's the nice thing about sequences, is there's not always one right way to do it. So you could come up with that rule in different ways, but I really like this method with my dn plus c. So that kind of sums it up for a few examples with writing the explicit rule for the arithmetic sequence. We want to move on and go ahead and talk about arithmetic series. Okay. So there's a great story about the formula for arithmetic series and one of a famous mathematician, and I'll share that with you when I return. But we'll just go ahead and we'll talk about what is the formula and then how we can use the formula. So formula for arithmetic series, because we're talking about a series, we're going to go out of the A sub n, where we're talking about a term in a sequence, and we're going to use S sub n, which is the sum of the first n terms of the sequence. And that formula looks like n divided by 2 times the quantity a sub 1 plus a sub n. So n is the number of terms you want to add. And then in this quantity here, we have the first term and also the nth term, okay, which is going to be like the last term that you want to add. So if you are adding the first 20 terms, then you want the 20th term right there. So that matches however many terms you're trying to add. This should look familiar from Algebra 2. We'll look at some examples here. We'll look at the first one. Find the sum of the finite arithmetic sequence. So finite meaning it has an end. Notice that after 19 it doesn't say plus ... Okay. And so I'm going to use that formula that we just had on the previous slide. S sub n equals n divided by 2 times the quantity a sub 1 plus a sub n. I'm going to think about, do I know what those things are? So n is the number of terms I want to add. And if you count these terms, 1, 2, 3, 4, 5, 6, 7, I have 7 terms to add. So I'm doing s sub 7 equals 7 divided by 2. And then I want to add the first term. Okay, well that's 1, so I'll put 1 in. Plus a sub n, which in this particular problem would be, because n is 7, I want to know a sub 7. So that will count out to be my last term. A sub 7 is 19, so I want to add 19 right there. Okay, the first term and the last term for the terms that you want to add together. S sub 7 equals 3.5 times 20. And multiply that out, you'll get 70 for the sum. Now, certainly on this particular problem, you could take your calculator and actually add up those numbers. but you could imagine if you want to add more than 7 terms, that would start to get a little bit tedious, and so this is a great way to avoid doing that. Okay, so a pattern that works for us. Let's also look at the next example, which is the sum of the integers from -10 to 50. So when we say the sum of the integers, I'm thinking, okay, I want to do -10 plus -9 plus -8 plus -7 all the way up to 50. And that's a good example of, I don't really want to have to add all those numbers together. So again, what I want to try to figure out is, how does that fit into my formula? S sub n equals n divided by 2 times the quantity a sub 1 plus a sub n. What's nice about this problem is -10 is going to be your first term, and 50 is going to be your last term. Okay, and I suppose the big question is, what is n? So how many integers are there from -10 to 50? So the way I always think about it, because I kind of have a hard time sometimes counting this, is I think, okay, from -10 to -1, that's 10 numbers. And then from 0 to 9, that's 10 numbers. And 10 to 19 is 10 numbers. So when I get up to 40, 40 to 49 is 10 numbers. So instead of having 60, I really have 61, because 50 is in the next set of 10 numbers. So my n value here is really 61. Okay? And that makes 50 a sub 61, or my last term that I want to add. So I could say the sum of the first 61 integers from -10 to 50 is equal to 61 divided by 2 times -10 plus 50, and that would be 30.5 times 40. And the sum there is 1,220. So probably the hardest part about those kinds of questions are making sure that you actually have the right first term, last term, value of n. Those are going to be the things that you're thinking hardest about. And then once you think about those things, you can plug them into the formula. We've got a couple other examples to look at real quickly here with our series. So my next example says, find the 30th partial sum for the arithmetic sequence, and then it gives a sequence, 78, 76, so on and so on. Okay. This one's worded a little bit differently than maybe we saw in Algebra 2. So when it says the 30th partial sum, it just means the sum of the first 30 terms. So basically, whatever that number is for partial term, that's telling us what n is equal to. Okay. Now, on this problem, I then can easily spot a sub 1, that's 78, but I maybe have to do a little bit of work to find my 30th term. So what I would do to find a future term that's a little bit further out is go ahead and write my rule. So really quickly, I'm going to write my explicit rule for this sequence. A sub n equals dn plus c, where c is equal to a sub 1 minus d. So c would be equal to my first term, 78, minus my common difference, and I can tell by the numbers here that my common difference is going down, so it's a negative. 78 minus -2, so c equals 80, and then a sub n equals -2n plus 80. There's my explicit rule for the sequence. And in order to be able to find the sum for the first 30 terms, I want to do a sub 30 equals -2 times 30 plus 80. That would be -60 plus 80. So the 30th term is 20. And then I can take that information and plug it into my formula for the series. So S sub n equals n divided by 2 times the quantity a sub 1 plus a sub n. That'd be S sub 30 because we're finding the 30th partial term, or partial sum, is 30 divided by 2 times the first term, 78, plus 20, the 30th term. And then that would be whatever 15 times 98 is. So the sum, or the 30th partial sum, is 1,470. So sometimes, in order to be able to find the sum of an arithmetic sequence, then you have to actually write the rule for the sequence so that you can plug it into the series. And last example is an application problem. Consider a job offer with a starting salary of $32,500 and an annual raise of $1,500. Determine the total compensation from the company through 6 full years of employment. So read carefully and figure out what information you've been given. 32,500, that's going to be my first term. A raise of 1,500, that's my common difference. Okay. I want to determine total compensation. So that would be all the salaries added together. So a series. And through 6 full years of employment. So that's giving me my value of N. So this is going to be very similar to the last problem. I might real quickly write the rule to find the salary after 6 years. Okay, if I were to do that, I would say, first of all, C is equal to 32,500 minus D, which is 1,500. So C is 3,100. Or sorry, 31,000. I'd be very sad if I was paid $3,100. And then my rule would be A sub n equals D, which is 1,500 times n plus 31,000. And then I could find my salary after 6 years. And some of you are probably like, well, I probably didn't need to write the rule there. I could have figured my 6-year salary. Also cool, so you could do it that way. So I find out that my 6-year salary is $40,000. Okay. And then I want to find the sum of all 6 years of salary. So I'm doing S sub 6 equals 6 divided by 2 times the quantity. It's going to be my first year salary, 32,500, plus my last year's salary, 40,000. And that's going to be 3 times 72,500. And that should equal $217,000. Oh, $217,500. Can't talk and write at the same time. All right, so there I go. You might have to think about in a word problem, okay, am I just finding a term in the sequence, or am I finding the sum of the series, and then use whichever formula is most appropriate to answer your question. So be thinking about those things. All right, that's it for your notes for today. You have an assignment. It's on your gold sheet. You should get out your textbook. You should be working. Share your textbooks with each other. And I will see you tomorrow to talk about geometric sequence and series. Have a great day.